Good morning, everybody. Welcome to this session and the first session of this morning in session 2. We are going to start off with Tyson because we are still battling to get the other guys online. So please excuse us for jumping ahead. Tyson, would you be able to join us now to give your talk?
Hi Tyson, we've sent you a notification to please accept it to join us on the stage.
Tyson, can you? There we go. Hello, Tyson. Good morning.
Good morning, Sandra.
You are welcome to share your screen with us and start your talk.
Okay, Windows.
D.
Okay.
Do you manage?
Yeah, I'm managed. Push. Network is slow.
Is your connection a bit slow?
Yeah, the connection is a bit slow.
All right, don't worry. So just to check, you've got your presentation in full presentation mode.
Yes, it's in full presentation mode.
Okay, so you are just battling to share.
Yeah, with the connection.
In the meantime, Tyson's going to talk about growing okra, an organic medium enclosed through system improves growth, yield, and water use efficiency.
Yes. Sure.
Tyson, do you need any help?
No, it's still the network is trying to connect.
Tyson, we can share slides for you and then you can just prompt us through to move to the next slide. We've displayed it on the screen. Can you see it?
Sorry?
Can you see your slides on the screen now? We've placed them on the screen. We can navigate them for you and you just tell us when to move to the next slide.
No, I cannot see the slides now. I think it's network.
Go out of presentation mode because Remo will share your slides on your behalf. So go out of presentation mode so that you can see our screen.
Okay.
Do you see your slides now there?
Not yet.
Angela will show your slides to us and you can continue with your talk and just tell her to move from one slide to the other.
Sorry?
Angela will share your slides on your behalf and all you need to do is just to tell her to move on to the next slide. Then we can continue and you don't have to try to share your slides anymore.
Okay. But problem is now the connection is this side. I cannot see the screen. It still say not responding.
Okay, but go ahead with your talk. She will share your slides. She's got your slides.
All right.
So you can just go ahead and start talking.
All right.
All right. So you can just start talking. Tyson,
Yes,
you can start your talk. We can see your slides.
you can see the slides.
Yes, we can. You just have to tell us when to move on to the next slide.
Are they moving?
They will be moving. Angela, can you move on one slide?
Asim, we're going to move on to your introduction. You can start with that slide and then tell us when you, there we go. Your introduction slides are on. You can talk to that slide so long.
You can start, Tyson.
It appears we've lost him completely. Would you like to proceed to the next presenter?
Yes, let's do that.
Sure.
Are we going to go back to Samuel or are we going to go on to Dr. Mupai?
Let's call Samuel.
Samuel, will you be able to share your screen with us now?
Yes, good morning. Can you hear me?
Hi, Samuel. Will you be able to share your screen?
Yes, let me just do it right away. Sure. Can you see it?
Yes, we can.
Okay.
It is not in full presentation mode, but I think due to time, we must move on.
Okay. Thank you very much. My name is Samuel Masogume, and I'll be taking you through a presentation entitled Tracking Chlorophyll Fluorescence as an Indicator of Crop Growth Efficiency in Amaranthus cruentus. The study was under the supervision of Prof. Jack Bernal, as well as the project manager from the Department of Agriculture, which is Mr. William Wakes. The introduction, there's been much of a talk regarding climate change, and we do understand that climate change is impacting crop production, and it will definitely impact crop production in the near future. Hence, the introduction of new crops, or there has been a renewed interest in the introduction and production of pseudo-grain crops such as Amaranthus cruentus. So the picture that is on your right, it does show the Amaranthus growing in the field. The adoption and the renewed interest in the production of amaranth is due to its ability of being used both for as a green leaf vegetable, as well as the grain that it produces, which is a good source of quality protein, as well as other micronutrients. And to put it into perspective, the major benefit of Amaranthus cruentus is its high content of the amino acid lysine. So if we take a look on the pictorial view of the Amaranthus crop which is growing, we can see that all the leaves are green. And one can assume to say, as long as the crop is green or the leaves are green, they are photosynthetically active and efficient. But the study seeks to understand if leaf age or the differences in phenological growth stages can affect leaf photosynthetic activity. Thus, the assessment of photosynthetic performance of different leaves of the crops is important, and this will also enable measurements on crop vitality. Hence, the study aims to study the effect of leaf age on Amaranthus cruentus, and we'll be using the novel non-destructive high throughput method, where we'll be measuring chlorophyll fluorescence induction kinetics. So I'll define photosynthesis, which is the major process which has led to primary production of biosphere. And we would understand that photosynthesis is driven by light, carbon, as well as water, which are the major constituents of this process. Hence, when a light strikes a chlorophyll molecule, let me just get a pointer. When light strikes a chlorophyll molecule, the light is either used by the plant in the process of photochemistry, and a portion of the light or a certain composition of the light is dissipated in form of heat or what is called chlorophyll fluorescence. Hence, chlorophyll fluorescence is a small fraction of dissipated energy from the photosynthetic apparatus, which is the chlorophyll molecule. Hence, from the studies have shown that energy conversion normally takes place with a high efficiency exceeding 90% for the absorbed quantum, which is 90% of the energy or of the light received is used for photochemistry, but 10% is dissipated either through heat or fluorescence. And studies have shown that there is a direct relationship between chlorophyll fluorescence and the photosynthetic efficiency of plants. To enable this assessment of crop vitality, measurements of chlorophyll fluorescence are vital. Thus, changes in chlorophyll fluorescence arising mainly from the photosynthetic system 2, which is the PS2, provides information on all aspects of photosynthesis and can be used to accurately probe photosynthetic performance of different leaves in the plant. So the instrument on your right is a plant efficiency analyzer, which is called a HandyPE.
Samuel?
Hello?
Samuel, this is Sandra speaking. I'm sorry to break up your talk now. Your talk is not in full presentation mode, so we cannot see your slides. Would you like to try and reshare it with us? The audience would really like to see your slides. You can continue from where you stopped, but just try to reshare it with us. So you must put it in full presentation mode. You won't be able to see us. You will only be able to see your presentation.
Let me just put it on full presentation mode.
Yes. And then reshare it again with us.
Okay.
I'm sorry to stop you there. I should have stopped you a little bit earlier.
And then I've put it on
Full presentation mode.
full presentation.
Then Windows D for desktop.
Windows D.
Together. Then you will
and
then you go at the bottom on the ribbon, you go back to that Google Chrome.
And then I say share.
And then you say share, that is correct. And remember to click on your talk, otherwise it won't move forward.
Okay, can you see it?
Yes, fantastic. Thank you very much. My apologies for stopping you there.
Okay, can I just go ahead? Oh, okay.
You don't, I think you can continue from where you were.
Okay, yeah.
Thank you very much.
I was just describing the plant efficiency analyzer, which is the NPE, that we used to measure chlorophyll fluorescence on dark adapted leaves. The leaves were dark adapted for an hour, and the instrument excites the electrons in the chloroplast through the emission of a red light impulse, and then we analyzed the chlorophyll fluorescence data using the JIP test or the OJIP fluorescence transient curves. So the basic chlorophyll fluorescence principles are based on the Koch's effect, which assumes that all photosynthetic material investigated so far show uniform features related to chlorophyll fluorescence emissions. Hence, a dark adapted leaf shows a fast polyphasic rise or a characteristic change of chlorophyll fluorescence, which is known as the Koch's effect, which is shown in this graph. Hence, we can see the polyphasic. Let me just put on the pointer. We can see the polyphasic phase, which is the OJIP curves. And this is in relation to the photochemistry or the photosynthetic process when an electron is reduced in the PS1, and as it moves from PS1 to PS2, this curve is developed. So the objective of the study was to evaluate the performance of different leaves on the Amaranthus cruentus with the aim of profiling leaf efficiency at different stages of growth on the same stock. We hypothesized that the photosynthetic performance of leaves on the same stock will shift with crop growth stage or phenological stages. Materials and methods. We planted Amaranthus cruentus at the Northwest-University under conditions which were free of abiotic and biotic stress. The plants were dark adapted for an hour, and a total of 6 measurements were taken on each leaf using the NDPA. Data which was collected, which I'm going to present, is the maximum quantum yield, which is the FV over FM, the PI ups, the PI total, and the driving force total. So you see, I plotted the graphs that I'm going to present. It's the pooled values of five samples. So I'm going to explain it in a moment. So you can see the Amaranthus crop, it has got the bottom leaves, which are green up to the fluorescence, where you are having the whole plant showing green leaves. But we do have partitions in terms of physiological maturity of the leaves, where we'll be having the early vegetative leaves, the late vegetative leaves, the early inflorescence leaves, as well as the late portion of the inflorescence leaves. Hence, we then divided the plant into quarters. So the plant was divided into quarters. So we had 4 quarters, with each having 5 leaves, which were put together to create or to get a one value, which we then analyzed and we are going to present. So also to add on, the Bbch scale, which is on your left, is the one which we used in terms of tracking the crop growth stages, where we have got the germination, leaf development, stem elongation, inflorescence stage. So we started our measurements at stem elongation, and then we ended them at seed development. Hence, we had hence we had the crop in those different stages. So moving on to results, I'll present the results as follows: the FV over FM, which is an indicator of the maximum quantum yield of PS2 chemistry, as well as the DRO, which is the efficiency with which an electron from the intersystem electron carrier is transferred to reduce end electron acceptor at the PS2 acceptor side. So we can see from the first graph that there was the leaves showed a high maximum quantum efficiency, of which quantum efficiency, it entails the maximum use of the energy or of the light that has been absorbed by the leaf. Hence, there was a maximum efficient of use in terms of the light that was absorbed by all the leaves, and it declined at the apical inflorescence due to booting. So during the stage of booting, the crop tends to have there is a physiological change from vegetative into the development of the seed. Hence, there is more of the assimilates being required by the plant. Hence, we can see that the first quarter and the second quarter of the leaves, which are mostly the bottom leaves, they resembled a decrease in maximum quantum yield, whilst the third quarter and the fourth quarter generally showed a spike in the maximum quantum yield. Also, taking a look on the DRO, which is shown here, with the efficiency with which an electron from the intersystem is carried, we can see that there was a shift. There was a shift in terms of the efficiency with which the electrons were transferred through the intersystems. And let me just show the PI ups. PI ups is one of the most parameter which showed us the differences in terms of leaf performance, where we are having the first 2 quarters of the leaves, which is the first quarter and the second quarter, showing high performance under the apical, during the apical inflorescence or the late vegetative stage, and it decreased over time due to leaf aging. But we can see that from the very same point at 9 weeks after planting, there is a spike in the third quarter showing its maximum PI total, which is the maximum PI total towards booting. And we can see that the fourth quarter of the leaves, which is the leaves which are more or less close to the inflorescence, they also showed their peak down at 12 weeks after planting. Hence, we can see that there is a shift in the rate at which, or there is a shift in terms of leaf performance as we move up the stalk. So the bottom leaves will be acting as sink leaves, while the top leaves will be acting as source leaves for the plant. Hence, we concluded that leaf age is an important factor that influences the fate of photochemistry due to this shift in photosynthetic performance at different growth stages, as well as plant photosynthetic performance shift from the bottom leaves towards the newly growing leaves, which is an indication of new leaves acting as sources, while older leaves shifting to being the stronger sinks for photoassimilates. This is the end of my presentation. I thank you. Hello, Sandra.
Well done. Thank you for your presentation. While we are waiting for Sandra, there we go. She'll conduct the Q&A with you now. Thank you.
Samuel, hello, can you hear me now?
Yes, I can hear you.
We have 2 questions for you. One question, the first one, why did you decide to use the Bbch scale?
So the Bbch scale is a standard scale that has been used on many crops, and it defines the phenological growth stages of the crop from germination, from actually seed development up until the crop is fully mature. Hence, to be able to classify, or to be able to identify the correct stage at which the crop is, we had to use the Bbch scale because it defines the crop stage, and you can be able to then relate to the crop to say where on the Bbch scale is my crop and which measurements should I take and which leaves are physiological. So the idea of using the Bbch scale was to standardize the process because we had a scale that we had.
Okay, thank you very much. There's one more question, and then I think we're going to move on to the next speaker. That will be Tyson. So Tyson, if you are going to be ready. Samuel, your final question. Why do you think the F and over Fm decreased at the apical fluorescence, while the D row increased at the same time? So why did the Fv over Fm decrease during apical fluorescence, while DR row increased at the same time? Do you have any speculations there?
So I assume that let me just go back. I think there is need to track. They actually all of them they decreased. So there is need to track the crop from 6 weeks to 14 weeks. So there was a progressive decrease as well as some increase in both parameters. So it wasn't just a decrease on the FV over FM coupled by a decrease on the DRO.
Okay, thank you very much.
I think that. Okay.
Thank you, Samuel, and thank you for persisting with us. Ladies and gentlemen, we are running a little behind due to technical difficulties. Our next speaker is then Tyson Mokgalabone. Tyson, are you ready for us?
If you can just put your camera and microphone on, we saw you appear again.
Yes.
Thank you, Tyson. We will share your slides on your behalf for you. Ezra's going to share the screen.
Can I share, please? I'll share it myself. Here they are. Can you see them?
No, we can't. Let me see.
There we go.
Yes, we can. You can go ahead.
Okay, good morning, ladies and gentlemen. My name is Tyson Mokgalabone, and I'll be presenting to you a research report entitled Growing Okra on an Organic Medium in Closed Trough System Improves Growth, Yield, and Water Use Efficiency, authored along with Dr. S.M. Pai, Mr. nwu-pukke, and Dr. A.R. Ndlala from University of Limpopo. Okra, which is scientifically known as Abalamatus esculentus, is highly nutritious and underutilized indigenous vegetable crop grown in tropical and subtropical regions. It is praised for its tender and immature pods that are consumed as vegetable. They are rich in proteins, amino acids, fat, fiber, vitamins, and mineral elements. It is a vital source of nutrients to reduce malnutrition, cholesterol, chronic disease, and assist in constipation. It is negatively affected by drought, which retards growth of ingot leaves and the edible pods. Ladies and gentlemen, fresh water and cropping land are becoming the most critical commodity nationally and internationally, which necessitated a need for a research on a non-drainable growing technique that will result in enhancement of growth, yield, primary and secondary metabolites on a relatively small area. OMET is a system that is more efficient in crop production with exceptionally high quality produced on a relatively small area. It is a climate smart production system that is environmental friendly with no water, no nutrient seepage because it is practiced under enclosed trough. It can be operated by anyone and reduce the cost of production. You don't need to be equipped with high technological skills to be able to operate this growing system. This picture shows you the okra plant that is grown under the OMET system. The aim of this study was the determination of the growth and yield attributes of okra grown under OMET system, with the objective being to investigate the effect of the OMET system on growth and yield of okra cultivated crimson spineless. In achieving the objective, the experiment was conducted in an open field under randomized complete block design with 3 replication and 12 plants per microplot, with both the OMET and the non-OMET. The non-OMET was used as a control to check if the OMET was indeed effective and efficient. This just shows you the randomized the microplots for both the OMET and the non-OMET. The OMET ones are the ones with the black plastic, and the non-OMET are the ones without the plastic. The methodology, okra seeds were sown in disinfected seedling trays and then irrigated to full capacity and waited for germination. In preparation of the OMET system, a plastic was laid out in 2 by 2 meter microplot and then supported with stainless steel and then filled with pasteurized loam soil, sandy soil, and hygro mix in a ratio of 2:1:1. And then after that, after filling the plastic with soil, the plastic was closed in a sandwich kind of a setup, and then holes were done on top of the plastic in 45 by 45 centimeter between the plants. In preparation of the non-omet, the 2 by 2 meter micro plot was measured, and then the soil, the prepared growing medium was, we used 30 centimeter pots to fill and filled it with the prepared growing medium, and then laid it out in 45 by 45 centimeter between the pots. And then after preparation of both the omet and the non-omet, 4-week seedlings were transplanted into the prepared and in the prepared holes, which were 45 by 45 centimeter, and then again transplanted into the pots. No pesticides, fertilizers, or herbicide were used in achieving the objective. Below is figure 4, is pictures showing you the omet and the non-omet. With the result and discussion. This is a picture showing you the omet and the non-omet grown okra plant, and then you can see the difference between the two. In the omet, the plant vigor is more as compared to the non-omet, and then you can see that the non-omet, the omet one also have more roots, more the leaf are larger, the more longest leaves. And then here is the stem diameter between the okra and between the omet and the non-omet. You can see that the omet grown okra has the thicker stem diameter as compared to the non-omet, which has thin stem diameter. This is a graph showing you the difference in the stem diameter and plant height. As you can see that there is an improvement in both the stem diameter and the plant height in the omet grown okra compared to the non-omet. And then this is a graph showing you the plant height and stem diameter over time, how they were increasing or decreasing over time. You can see that as initially the plant height for the omet was almost the same as the plant height for the non-omet, but as time goes on, as you can see in week 5, the plant height for the non-omet is taller than the one in the non-omet, and the trend continues like that. The omet grown okra becomes taller than the non-omet, and again the stem diameter of the omet grown okra is more thicker as compared to the non-omet grown okra, which is thin. This is the difference between the leaf size of the omet grown okra and the leaf size of the non-omet grown okra. You can see that there is an increase into the leaf size of the omet grown okra as compared to the non-omet. And then this is the graph showing you the average longest leaf length of the okra grown in the omet as compared to the one grown in the non-omet. And even the biomass, you can see that there is an increase in the biomass of the okra grown omet versus the non-omet. These are the pods. You can clearly see that there is difference into the pod length of the omet grown okra as compared to the non-omet grown. And then this is the pod yield mass, a graph showing you the pod yield mass of the okra grown omet and the non-omet, and the number of pods per plant into the omet. You can see that there are more pods in the omet grown okra as compared to the non-omet. Even the days to maturity, they decreased in the omet as compared to the non-omet. This is the amount of water that was irrigated into the omet as compared to the non-omet, and then they were recorded and then we did the cumulative irrigation water. You can see that more water were irrigated into the non-omet as compared to the non-omet. To discuss, we all know that there are various yield components that includes your number of branches per plant, your plant height, your fresh pod length, and the width, the number of pods per plant, and pod width, and the pod weight that influence pod productivity in okra. At harvest, yield components, as you can see, they were twofold higher in the OMET as compared to the non-OMET treatment. Even the growth attributes such as your plant height, which was at 152,1, which had an average of 152,1 centimeter, was higher as compared to the non-OMET, which had an average of 134,2 centimeter. The taller plants in the OMET were crucial for accommodating more number of pods on the main stem. Probably there is a positive relationship between the plant height and the fresh pod yield. And then if you check the stem diameter in the OMET, it's also taller, as we observed in the graph. It's having an average of 16.9 millimeter compared to the 7.6 millimeter of the non-OMET treatment. And then the thicker stems in the OMET, the thicker stem in the OMET compared to the thin stems in the non-OMET, probably they were crucial for supplying both the water and nutrients to the branches and to the pods. The OMET system, the variation in the stem diameter between the OMET and the non-OMET might be attributed to the maximum plant height, which captures maximum sunlight for the photosynthesis, which results to the formation of maximum photosynthase that accumulated in the stem. And this might be the reason behind the leaf length, the longest leaf length, which is in the OMET system. And then again, the OMET system enhanced physiological maturity, which was 15 days earlier than in the non-OMET. It is disposal of lower irrigation. How did we see this physiological maturity? You see it if the 50% of the pods in a treatment, they are more than 30 centimeter in leaf length. The trend that was observed in the research was that with an increase in a stem diameter, there was increase in the plant height, which resulted in more branches per plant, thus resulting in that plant having the longest leaves, thus resulting in that plant having more number of pods with longer pod length as compared to the plants with thin stem diameter, which were having the smaller plant height, and then the leaves were also smaller, which in this case were the non-OMET. The present study determined the efficiency of the OMET system to improve the growth and the yield attributes of the okra using less water. As I said, that fresh water and cropping land are becoming the most scarce and expensive commodity. Mostly this affects the small-scale farmers. So I recommend this system to the small-scale farmers to enhance productivity and maximize profit while minimizing production cost without using high technological skills. This system can be operated anywhere by anyone. It doesn't need to be equipped with any skills. And it conserves water. And then again, it conserves water while the ecological interaction is harmonized because it doesn't interfere with the ecological interaction. The pods for both the OMET and the non-OMET will be subjected to testing and analysis of both the primary and secondary metabolites to check if there was a variation or enhancement of both the primary and secondary metabolites in the OMET as compared to the non-OMET. That is the work that is being done now in the center. I would like to acknowledge the University of Limpopo, Department of Science and Innovation for funding the study, and SAAB for giving me the platform to share my research with you. Thank you very much, ladies and gentlemen.
Thank you, Tyson. I can see that you are very enthusiastic about this project. There is one question from the audience. They would like to know, did you subject your data to any statistical analysis? Did you determine any significant differences?
Yes, it was subjected to statistics 10.0.
All right, thank you very much.
Okay.
Thank you for your talk, Tyson. You can stop sharing your screen and then we can move on to our next speaker.
Okay.
Ladies and gentlemen, we are running a bit later on our schedule. It's about 10 minutes later, and that was due to connectivity problems. Our next speaker is Dr. Mupai, and we'll be speaking about the improvement of yield and growth in Amaranth species using the organic medium enclosed trough system. Dr. Mupai, are you available? Dr. Mupai, are you available?
Sandra, we've sent a request through to Dr. Mupai, but yeah, Dr. Mupai, if you've received the request from us, please accept it and just activate your camera and microphone to join us on the stage.
There we go. Thank you very much. Oh, fantastic. Thank you, Dr. Mupai. You are welcome to carry on.
Dr. Mupai, you are currently on mute. If you can press Windows D button. There we go. There we go. We can see you now. Thank you. You can present.
You are welcome to proceed. We have introduced you. Please carry on. We can see your slide. You can start. Please go ahead.
Okay. Good morning, ladies and I am Mupai Class, and I will be presenting to you my research report entitled "The Improvement of Yield and Growth under Organic Medium Enclosed Trough." Amaranth species are a popular group of consumable indigenous vegetables that are known worldwide. Amaranth is a collective name for the genus Amaranthus of the family Amaranthaceae. They are known to be rich in primary and secondary metabolites, and they have the potential to combat the crisis of food and nutritional insecurity. Yet, they are not usually produced here in South Africa. They usually occur voluntarily as weeds during summer seasons. Their production is very limited to small-scale farming, and it is also worsened by the effect of global warming and the water scarcity, and also the soil nutrient loss. Below are the 3 amaranth species that were used during this study. The first picture is a picture of Amaranthus cruentus. The second one is Amaranthus cordotus. The last one is the unknown amaranth species, which we will have to go and find out its scientific name. Modern agricultural farming innovations should be aimed at increasing the yield and sustainability. Organic medium closed in trough system is a non-drainable farming technique that was developed in 2012 by Helmut Rohrer. Till today, it has not gained popularity in crop production, because most farmers believe that it is somehow impossible for crops to grow without drainage. Some of the benefits of the OMED system include low technological innovation. It eliminates water and nutrient loss. It prohibits the high evaporation rate. It is also adaptable, requires no high-tech skills. It is 100% organic and environmentally friendly. Below is a picture of the OMED system. This OMED system, it is a brilliant low technological innovation for water and nutrient conservation. Hence, you know, we have a crisis of nutrient loss and water scarcity. Adoption of this system can enhance vegetable productivity in low input farming. The aim of this study was the evaluation of OMED system on the growth and yield attributes of 3 amaranth species that I have mentioned previously, with the objective to investigate the effects of OMED system on plant height, stem diameter, and fresh biomass of the 3 amaranth species. This research was conducted at the Greenhouse Biotechnologies Research Center of Excellence at the University of Limpopo. And RCB, the randomized complete block design, was used as a research design. In the OMED system, in greenhouse benches, whereby loam, soil, and sand were mixed together with hydromix at a ratio of 2:1:1 respectively, and filled the underlaid plastic, which was laid at a depth of 25 centimeters in the greenhouse benches, and then the plastic was tenfold to form an enclosed trough. The walls were made at a row spacing of 20 centimeters by 20 centimeters between the plants. Preparation of seedlings and transplanting. The seeds were obtained from the ARC VIMP in Pretoria, and the seedlings were prepared by sowing the seeds in the disinfected seedling trays filled with the hygromix, and they were irrigated to field capacity. At a 4-leaf stage, after 4 weeks of preparing the seedlings, they planted into the OMED at the top there, and then the non-OMED, which was done in the microplots in the 25 centimeter pot. The seedlings that were transplanted were then irrigated when necessary, referring to the moisture sensors. The mean separation for significant treatment were achieved through a t-test at the significance level of 5%. That analysis was done using a computer statistical software known as the Statistics 10.0. Results and discussion. The figure here is a graph showing the plant height of the 3 amaranth species grown under OMED and non-OMED. As you can see, the black bar graphs there represent the amaranth species which were grown under the OMED system, and the gray ones represent the amaranth species which were grown under the non-OMED system. And it is clear that the amaranth species which were grown under the OMED system, they grew taller than the ones which were grown under the non-OMED system. Since amaranth is a C4 plant, therefore it requires sunlight for photosynthesis, more sunlight for photosynthesis than the other C3 plants, which is why it grew taller, to access more sunlight, hence it was grown under the greenhouse. This is the graph showing the trend of the 3 amaranth species. Graph A showing the trend of plant height over 8 weeks of the Amaranthus cordatus grown under omet and non-omet. As it is visible there, initially they were the same. The plant height were the same, and then they started the one grown under omet started to grow taller than the one grown under the non-omet at week 4. It is clear on week 4 going upward, and the same trend is observed at graph B for the Amaranthus cruentus. And the graph C, at graph C, the unknown Amaranth species, the ones that were grown under the omet grew taller. They started showing respond at week 5. They grew taller than the ones grown under the non-omet at week 5 up to the last week, which is week 8. This figure 5 showing the stem diameter of the 3 Amaranth species, again grown on omet. As you can see, it shows a significant difference. As you can see, the stem diameter of the Amaranthus species that were grown under the omet are thicker than the ones that were grown under the non-omet. That can be due to, since the last paragraph, the graph showed that the height, the plant height of the ones that were grown under omet, they were higher, they were taller. The stem diameter also proportionally, positively, it associates with the plant height so that it can support the plant significantly. This is the trend of the stem diameter over 8 weeks, where there the graph A is the trend of stem diameter for Amaranthus cordatus, and graph B is for Amaranthus cruentus, and the last graph is for Amaranthus unknown species. Figure 7 is the graph showing the fresh biomass of the 3 Amaranth species grown under omet and non-omet. The fresh biomass of the Amaranth grown under omet is higher than the one of the Amaranth species grown under the non-omet. This can be due to, since I said that the omet system conserves water and nutrients, unlike the non-omet. These plants grown under the omet, they had more of the nutrients from the growing medium as it has conserved them than the ones that they may have probably leached during irrigation. As it is observed, Amaranth grown under the omet, it is doing better, far much better than the one that is grown under the non-omet. As you can see, it is twofold higher on each species. This is the graph showing the longest root length of the 3 Amaranth species. Here, the omet system did not show, didn't increase or enhance the longest root length of the 3 Amaranth species than the non-omet. The non-omet here was doing better because in the non-omet, the nutrients are conserved, therefore they are kept closer to the rooting zone. Therefore, the plants grown under the omet will not grow taller, will not have longer roots because they can access the roots, the nutrients closer. Unlike on the non-omet, which had longer roots, they had to grow taller so that they can access the leached nutrients, try and access, feed themselves and support the plant. Here the omet grown Amaranthus cruentus and Amaranthus cordatus didn't have the long roots, unlike the one of Amaranthus unknown species that was grown under the omet. It had longer roots. That can be due to the growing habit of these unknown species. These are the statistical analysis of plant height, stem diameter, fresh biomass, and longest root length in all the 3 Amaranth species. But the table here, table 1A, shows the statistical analysis for Amaranthus cordatus, and it is visible here. They are highly significant at a P is SP is less than 0.05. The same applies to the second Amaranth species, which is Amaranthus cruentus. All the plant variables are significantly different, non-omet and omet. This is the last table, table 2B, C, table 2A, I mean, which shows the of the Amaranthus unknown species, and are also significantly different. As you can see, the P values there of the plant height, stem diameter, fresh biomass, and longest root length are less than 0.05. They are highly significant. Therefore, it means that the omet system is far much different in terms of increasing the yield and growth of these Amaranth species than the non-omet system. This is the land graph showing or representing the amount of water utilized weekly per plant over a period of 8 weeks. Initially, when they were transplanted at first week, the amount of water utilized was the same, but as time goes on and the plants are growing, at week 2, the amount of water utilized by the plant in the non-omet was higher than the one that was utilized by the one in the omet system. That can be due to the irrigated water. The initial amount of water that was irrigated in the omet system was conserved. Hence, the omet system eventually eliminates high evaporation rate and water seepage. Therefore, that's why second week, the amount of water utilized by the plant in the non-omet is higher and is getting higher as the weeks goes by. And then for the ones that in the omet, as it gets higher, because the plant is growing and then it needs more water. But unlike in the non-omet, the water in the omet is conserved and used efficiently and effectively. These are just a comparison between the 2 systems, which is the omet and non-omet system, whereby the omet system increased the plant height of each Amaranth species significantly, but it increased mostly the plant height of the unknown Amaranth species by 41.2%. And on stem diameter, the increased the stem diameter of Amaranthus again at about 32.4 by 32.4 than the non-omet one. And the fresh biomass, the highest fresh biomass was obtained from Amaranthus cruentus by 62.7% increase than the non-omet one. The rooting length, the omet only increased the unknown Amaranth species rooting length by 9.1, whereas on the other Amaranth species, it did not enhance the root length than the non-omet. And the water utilized by the plant per week over 8 weeks was far less in omet than non-omet. These are the pictures that support what I've been saying and illustrating on the graphs. Illustrated on the graphs, as you can see, on your left you have the non-omet plant-grown Amaranthus cordatus, and then on your right is your omet-grown Amaranthus cordatus, and you can significantly see the difference in terms of height, biomass, diameter, the root length, and all. It shows that the omet, it is better than the non-OMED system. It is clear here, as it is shown, illustrated by the pictures. In conclusion, I will say OMED system significantly enhance the growth and yield of the 3 amaranth species, significantly using less water than the non-OMED. This system can be adopted in low input farming systems, including in limited irrigation water supply. OMED is a brilliant farming technique that can overcome the future estimates of water shortage and nutrient loss, soil nutrient loss. Therefore, it is suitable for small-scale farmers for commercialization and specialization. There is a need to expand the scientific research on the effects of OMED system on vegetables, so that we can explore how the OMED system affect other indigenous vegetables, consumable vegetables. The future prospects of this study will be the nutritional analysis and analysis of secondary metabolites. And I would like to acknowledge the University of Limpopo, Department of Science and Innovation, and SAAB. Thank you.
Thank you very much. We have time for one question. There is a common question from the audience. Have you compared the OMED-grown plants with field-grown plants? Did you do any comparison?
Yes,
Can you hear me now?
Yes.
There is one. Can you hear me? Thank you. There is one common question. I'm only going to allow one question, and that is: have you compared the OMED system with plants grown in the field?
No, I haven't compared the OMED system.
Okay, there's quite a few of the audience that feel that that should be checked. Because it can cause a difference in the discussed parameters. So I think thank you to the audience for making those comments. There are other comments available as well, and we will send it on to you. But I think for now we should move on to our next speaker. Thank you very much.
Thank you, Sandra.
Our next speaker will be Dr. Mpai. And she will be speaking on the vegetative growth response of common consumed vegetables in response to different concentrations of amino acids based on the biostimulant. Good morning, Dr. Mpai.
Good morning, how are you?
Fine, thanks, and you? You're welcome to share your talk with us.
Do you see my slides?
No, we don't. What you have to do is to put your presentation in full presentation mode. Can you hear me?
Yes.
So put your presentation in full presentation mode. Then press Windows D, D for desktop.
Yes, I did that.
Okay, now you have to go back to the bottom at the bottom, yes, and say share. No, we don't see it. So go to the bottom and go back to Google Chrome. So is your presentation in full presentation mode?
Yes.
All right, there we go. Now we can see it. Yes, fantastic. Thank you. You are welcome to proceed.
Okay, thank you. Good morning, all. My name is Makaleng Mpai. I'm a postdoctoral fellow in the University of Limpopo, and I'll be sharing to you today my research project entitled Vegetative Growth Response of Commonly Consumed Vegetables to Different Concentrations of an Amino Acid-Based Biostimulant. Are commonly consumed vegetables in South Africa, which contributes to the food security and also to the overall, as shown in figure 1 highlighted in however, in the recent or in the past decade, there has been a decline in the production of these leafy vegetables, mainly due to the negative effects of global warming, including the excess extreme heat conditions and cold fronts. So in response to these effects, we have seen the adoption of chemical fertilizers, including the nitrogen fertilizers, which is usually used in the leafy vegetables to improve the crop production. However, we know that these chemical fertilizers, they also contribute to the food insecurity and rise in this global warming. If we may recall that the application of these synthetic nitrogen fertilizers, it has been associated with the accumulation of non-nutritive compounds such as nitrates and nitrites, which if taken in excess may be of health concerns to humans. Now, a greener solution to low crop productivity can be through an amino acid-based biostimulant, a phytostim. This product is commercially available and it is made up from a moringa plant extract, and also it contains 22 different amino acids. Taking you through the role of amino acid role in the plant growth. The amino acids are usually associated with the improved rooting system of the plants, of which the improved rooting system improves the water and nutrient uptake, of which ultimately improves the vegetative growth of vegetables. The objective of this study was to evaluate the impact of different concentrations of phytostim biostimulant on growth attributes and yield in lettuce and Swiss chard. What we did was we started by preparing the seedlings, and only healthy seedlings were selected. We selected seedlings in cultivar Lara and cultivar Elsa, which were cultivars of the lettuce, and we also used the food hawk giant, which was the cultivar for Swiss chard. The seedlings were transplanted following the complete randomized block design with a spacing of 30 by 30. And then the application of the phytostim biostimulant were applied at different concentrations, including 1, 3, and 6% at 14 days interval. And then our control was not treated with this phytostim biostimulant. And then we left the seedlings to grow up to 30 and 50 days for lettuce and Swiss chard respectively. At termination, we measured the fresh biomass, the plant height, the number of leaves per plant, and the root length. And then we subjected the data to the statistical analysis using the LSD to separate the means. And also we were using the statistics package, the statistics package 10. In our results, we found that the application of 3% phytostim biostimulant improved the root length in both cultivar Elsa and cultivar Lara. Furthermore, as compared to the untreated and 1% biostimulant. In addition, the application of 6% phytostim biostimulant improved the root length to such an extent that it was higher than those level of untreated and 1% dose application. The same trend was observed also in Cultivator. Similarly, in plant height, we observed that the dose of 3% was outperforming the other doses and also the untreated in both Cultivator and Cultivar Elsa. And we also observed that application of 1% and the untreated samples showed a retarded growth, or we had shorter plants as compared to those that of the 6% dose. The same trend was also observed when we checked the number of leaves per plant. We observed that the 3% also encouraged the formation of leaves on the lettuce plant, as in both Cultivar Elsa and Cultivar Lara. We also observed that the 6% in Cultivar Elsa improved the growth or the number of leaves as compared to the untreated and 1% dose. However, in Cultivar Lara, we observed that the 6% showed similarly growth to those of untreated and 1% dose. When we checked the biomass, we found that the overall biomass of in plants of Elsa and plants of Lara were significantly higher in samples that were treated with 3% biostimulant. And we found that the percent in Cultivar Elsa outperformed the samples of 1% and untreated samples. However, in Cultivar Lara, we observed that the application of 1% improved the growth as compared to biomass as compared to that one of 6%. This also shows that both 1% and 6% doses shows irregularity of growth parameters in these lettuce and in these lettuce cultivars, meaning that they are really not the optimum doses for this. They somehow retard growth or may give irregular growth attributes. When we move to the Swiss chart data that was obtained, we realized that the root length was improved. Also, the number of leaves was improved in the application of 3% dose as compared to those of the untreated and 1 and 6% doses. We also observed here that the application of 6% and 1% showed a retarded root growth as compared to those of the untreated, as compared to those of the 3%. The last graphs shows the plant height and the biomass of the Swiss chard plants. Here we also see that the 3% is working for the plant height and for the plant biomass, and the 6%, 1 and 6% also they retard growth, or they are showing irregularity in the growth pattern. The untreated samples were also showing in the untreated samples showed a lower plant height as compared to the other doses of phytostim biostimulant. And then when it comes to the biomass, we observed that the untreated samples showed to have similar values of the biomass with that one of the 6% dose. The the results found herein suggest that the different concentration of the phytoestin biostimulant are the main, they are very critical in plant production. So it is very important for us to optimize the concentration of the phytoestin biostimulant before application. So these results may be different if we check another fruiting plant such as tomato or bell peppers. And the results herein, however, they are in dispute. They are in dispute with those results that were found by Ken et al. 2019, which they mentioned that the application of 0.2 milligram per liter resulted in an increased plant and root growth. So here we found that 3% is working. However, there are discussion which also works for, which also I believe that is the mechanism which has occurred in this, our result is that due to the improved rooting system that we saw that the 3% improved the rooting system. We also say that the 3% improved the rooting system, which ultimately improved the water and nutrient uptake, and then improved the vegetative growth of the plants. So in conclusion and recommendation, I recommend that application of 3% phytoestin biostimulant improves the root length, leaf numbers, the plant height, biomass in lettuce cultivar and cultivar Elsa, as well as in Swiss chard. And we are saying that the application of 1 and 6% may somehow inhibit the growth, the optimum growth. And then this study has authenticated the efficiency of 3% that was recommended on the phytoestin biostimulant label. At this, I would like to acknowledge the following organizations: the DSI, the NRF for funding us, and also the University of Limpopo. We would also like to acknowledge the SAAB for this platform to present our research. And I thank you.
Thank you very much, Simakale. Can I ask you, can you speculate why the 6% did not cause improvement of growth? Is there any specific reason why you think, or would you like to speculate why only the 3% worked better?
The 6% was in some of the reports that I have read, they suggested that, or they that lower concentrations of an amino acid-based biostimulant works more than the higher concentration. I think that the 6% was more higher concentration and it inhibited growth. I think the more the amino acid-based biostimulant, the more it does not work. So what we can do there is to check the metabolomic studies and to see what are they in the concentration. Then we will be able to speculate well the mechanism that is happening there.
There is one question from the audience. The question is, what would the ingredients in the biostimulant that is contributing to growth of the plants? What would the ingredients in the biostimulant that is contributing to the growth of the plants? So do you know what the ingredients are in the biostimulant?
The ingredients yes, we know the ingredient. We have got the methanine, the alanine and all those kind of essential amino acids. So
it's only the amino
I'm
acid.
at a position to speculate which one worked what, but what I know that they were working in a group of 22 amino acids, but it's only amino acids that are there, no any other compound that is not an amino acid.
Okay, fantastic. Then there's one more question. Are you planning to measure any physiological parameters?
Yes, we will be working to do the ascorbic acid, because we know that the ascorbic acid, they are usually the ones that can speculate a mechanism of what could have happened in the growth of the inhibition in the 6% and 1%. So we'll be doing different phytochemicals, and we the color, because it looks like those that did not, those of the 1% and 6%, some discolorations, and that may be not be preferred by consumers during retail marketing. So those are the things that we will be checking.
Okay, thank you very much. We enjoyed your talk. Thank you.
Thank you.
You can stop sharing. Our next speaker is Happiness Nwu-pukke, and he will be talking on drought stress and heat stress decreases the phytochemical efficiency of Amaranth species. Happiness, are you ready to join us? Happiness, can you join us? Let's see if there's a problem.
Happiness, if you can just activate your camera and your microphone at the bottom of your screen. We can see that you accepted the notification to join the virtual stage.
There you are. Hello, Happiness. Thank you very much for joining us. You can share your screen and then you are welcome to proceed.
Okay, let me go. Then, okay, let's go. Okay, let me try to share it. I've already opened it. Let me just go.
Okay, so remember to keep it in full presentation mode.
Okay.
Then Windows D.
Windows D.
Then at the bottom you will see a ribbon and you will go back to the Chrome icon where the link is for us for the conference.
It seems like I'm struggling to get to that. Let me just...
What we can do is we can share the slides from the platform side, and then you can just talk and just tell us when to move to the next slide. We can also...
Okay, that would be great.
Angela, will you be able to share Happiness slides? There we go. So we can see your slides.
Okay, thanks a lot for that. Okay, the title of this study is Drought and Heat Stress Decreases the Photochemical Efficiency of Amaranth Species. You can go to the first slide. So the effects of climate change are more visible than ever before on the African continent. And the climate change is progressively resulting in high temperatures and drought, and these stressors are among the main environmental stressors that cause starvation in underdeveloped areas. They are projected to become more frequent and intensified in many regions, including the Southern Africa. This region has fragile agricultural system and frequently experiencing the combined effects of severe drought and high temperatures. So the combination of these stressors disrupt plants' photosystems and changes chlorophyll A fluorescence kinetics, and is expected to be the same for Amaranth species. Amaranth species has high nutritional value and has been shown to thrive in stressed conditions. And some Amaranth species have also been shown to have essential pharmacological properties against cancer. So the aim and objectives of this study was to determine if the JRP test parameters can be the most sensitive and efficient tools to quantify the combination of drought and heat stress in Amaranth species. Secondly, was to analyze the variability in interactive responses of photosynthetic parameters and other biochemical parameters to drought and heat stress. Lastly, was to determine if drought and severe heat stress could induce downregulation of the photochemical activities in Amaranth species by deactivating photosystem 2 reaction centers. So, material and methods. 4 weeks after emergence, the plants were subjected to drought stress or 10% field capacity and different temperature regimes ranging from 30 to 40 degrees Celsius for 2 hours. The kinetics of the polyphasic fluorescence rise indicating quinone A reduction was measured in vivo using the MP fluorometer as seen on the picture on 1 hour dark adapted leaves. Measurements were taken at 4 different spots on the adaxial surface of 3 fully developed canopy leaves of 3 plants per treatment. Measured photo-induced transient readings were analyzed by MP plus data analyzer version 1.0. You can go to the next slide. Results and discussion. Firstly, what I will do, I will firstly introduce you to these 4 parameters, of which I would understand most of you it will be something new to you, and of which it's very important that you both know these parameters and what it entails and why we choose these parameters. The first parameter, which is RC over ABS, is the reaction center density on chlorophyll basis. The second one is the probability that an absorbed photon will be trapped by photosystem 2 reaction center and it will reduce 1 quinone A. The third one, the efficiency with which the electron moves into the electron transport chain further than reduced quinone A. And lastly, the probability that the electron was transported from reduced plastoquinone to the electron acceptor side. So on the first parameter, it was noted that this first parameter, or all these 4 parameters, I would say, were all sensitive to heat at 40 degrees Celsius and the combined effects of drought and heat stress, as seen in figure 1B, D, F, and H. Though the probability that the absorbed photon will be trapped by photosystem 2 reaction center and the probability that the electron was transported from reduced plastoquinone to the electron acceptor side of photosystem 1 were less sensitive to heat stress under well-watered conditions, as seen in figure 1D and H. Further, the most sensitive parameter of the electron transport chain to the combination of drought and heat stress appeared to have been the probability that an absorbed photon will be trapped by the photosystem 2 reaction center and it will reduce quinone A and the reaction center density on chlorophyll basis, which decreased by 70.3% and 69.7% in Amaranthus caudatus and Hypochondriacus, respectively, as seen in figure 1B and F. So these observations directly suggest that the higher decline under drought and heat stress indicated that these stressors damage the photosynthetic apparatus of this species. In this study, drought and heat stress at 40 degrees caused a decrease in the photochemical quantum yield of the photosystem 2 in A. caudatus and A. hypochondriacus, as seen in figure 1D. So consequently, a decrease in the probability that the absorbed photon will be trapped by the photosystem 2 reaction center will reduce 1-quinone A was considered an indication of damaged photosystem 2 complex due to photoinhibition. This distribution reduces the inefficiency with which an absorbed photon could be captured by the reaction center of the photosystem 2. Besides, the decline in RC over ABS and the probability that an electron moves into the electron transport chain further than reduced quinone A, and the probability that the electron was transported from reduced plastoquinone. These values further supported the decrease in or decline in this value, further supported the occurrence of photoinhibition in A. caudatus and hypochondriacus, as seen from figure 1B to H. And as it and this indicated a decrease in the electron transfer across the intersystems to the final acceptors of photosystem 1. On the contrary, higher values of all these 4 parameters were observed for Amaranthus cruentus and spinosas under similar conditions, as seen in figure 1A to H, suggesting the stability of the reduction of photosystem 1 final acceptors, photosystem 2 structure, and the intersystems. Therefore, A. caudatus and hypochondriacus appear to lack adaptive mechanism to tolerate drought and heat stress. So, as you can go to the next slide. You can go to the next slide, please.
Angela, can you? There we go. Thank you.
Okay, usually I would prefer to focus on table 2, as is the one which has more explanation and comparing the interactive effect of the combined effects of this drought stress. Go to table 2.
Next slide, please. There we go.
Okay. Firstly, what I will focus on, I'll firstly focus on the first parameter, and I will also firstly introduce everyone on this parameter, which is the maximum quantum yield of primary photochemistry. And therefore, the values of this parameter, or the values of the maximum quantum yield of the primary photochemistry, or FV over FM of the photosystem 2, is regarded as a sensitive indicator of the plant's photosynthetic performance exposed to heat stress. Drought and moderate heat stress had an insignificant effect on the potential quantum efficiency of the photosystem 2, as seen on table 2. This confirmed the high stability of the potential photosystem 2 photochemical efficiency during drought and moderate heat stress. It was also noted that when the temperature was at 40 degrees, there was a substantial decrease of this parameter under drought stress in A. caudatus, where there was a 69.8% decrease, and in hypochondriacus, there was 73.7% decrease. This was an indication of the inhibition of the photosystem 2 activity, disruption of photosystem 2 antenna complex, and impaired regeneration ability of ribulose 1.5 biphosphate. Thus, the damage to the photosystem 2 structure by drought and severe heat stress blocked the photosynthetic electron transport chain connecting the photosystem 2 and photosystem 1, which has led to the reduction on the values of FV over M ratio. Secondly, the second parameter that we are also going to focus on is the RE over RC, which is the specific energy flux extracted from the OJIP test related to the reduction of the final acceptors of the photosystem 1. So the decrease on this parameter on A caudatus and hypochondriacus under drought stress condition for all the temperature regimes as seen on table 2 could be attributed to a decreased electron capacity between reduced quinone A and photosystem 1 electron acceptors. However, the increase observed in A cruentus and A spinosas, as seen also in table 2, under similar condition could infer an increase in the IP phase to the OJIP transient, which is genotype dependent. Similar results were reported by Okram et al. 2009 and Umar et al. 2019 on barley varieties and sunflower cultivars, respectively. So the increase in this parameter as the temperature increased in A cruentus and A spinosas indicated that heat stress under both conditions, as seen in both table 1 and table 2, did not disrupt the electron transport beyond reduced quinone A to the intersystem of electron acceptors. This further suggests that drought and heat stress activated adaptive mechanism in A cruentus and A spinosas. Lastly, we are going to focus on the photosynthetic index, which is the PIABs and the PI total. So both A caudatus and the hypochondriacus showed higher sensitivities to drought and heat stress, as both PI total and PIABs decreased by 50% and 100% respectively at 40 degrees Celsius, as seen on table 2. So on the other hand, A cruentus and A spinosas decreased by 10 and 20% respectively under similar conditions. So higher values of PI total and PIABs observed in A cruentus and A spinosas indicated photosynthetic apparatus' ability to increase the potential energy conservation. The PI total parameters encompass the increase in the prospect that the electron from the intersystem moves to reduce the final acceptors on the acceptor side of the photosystem 1. You can move to the other slide. In conclusion, based on our results, it can be inferred that A cruentus and A spinosas have better adaptive mechanism to tolerate drought and heat stress than A caudatus and A hypochondriacus. This study demonstrated that photosynthetic apparatus of Amaranth species were not affected by moderate heat stress, which is 30 and 35 degrees Celsius in this case, and it means that all species had higher temperature tolerance level and should grow well in hot areas. Among the discussed parameters, PI total and PIABs were observed to be most sensitive to different temperature regimes and drought stress, as they represent the overall behavior of photosystem 2. So detailed drought and heat stress tolerance studies of this species cultivar remain necessary to correctly identify cultivars that are suitable for arid and semi-arid regions in the SADC region. Next slide. The last one. Thank you. And I would like to thank Northwest University for offering me this opportunity.
Thank you very much, Happiness. That was very interesting talk. There are 2 questions from the audience. Your first question is, the audience would like to know if drought at 10% field capacity is not a bit extreme. Why did you choose this stress level?
Okay, this stress level was very necessary so that there can be a clear distinction between well-watered and drought-stressed plants in this case. Because once you have a 20% field capacity, some plants tend to recover quickly and it can interfere with your chlorophyll fluorescence measurements, wherein you might fail to identify well-watered and drought-stressed plants.
Okay, thank you. There's one more question. Which cultivar will you recommend to be planted in hot, dry conditions?
As our study has clearly indicated, A. cruentus and A. spinosas would fit perfectly well on dry areas.
Thank you. Thank you very much, Happiness. Thank you for your talk. You are welcome to stop sharing, and then we can move on to our next speaker.
Thank you.
Good morning, Kamogelo. Kamogelo Tefo is our final speaker for this session. The title of the talk is The Response of Onion to Amino Acid-Based Plant Biostimulant. Kamogelo, can you hear us? Can you join us? Kamogelo, are you there? Yes, thank you. You're welcome to share your talk with us.
Good morning.
Hello.
Good morning. Can you hear me?
We can hear you. You can share your talk, your presentation, and then you are welcome to proceed.
Okay. Yes, let me just share my slides now.
Yes. Do you need some help with that?
No, I'm just getting a problem a little bit, just minor.
If you've uploaded your slides, we can also share it on your behalf.
No, let me just try for the last time.
Okay. So we can see you. If you can just share your slides.
Yeah. Thank you very much for the platform. Can you hear me?
We can hear you clearly. We just don't see any presentation.
Okay, thank you. Okay, you can see my PowerPoint slides, miss.
No, we don't see any slides.
Okay. You don't see the slides?
No, we don't see your slides. Please try to share again. You have to go to, no. You have to go to full presentation mode.
Okay.
Once you've gone to full presentation mode, you press Windows D, D for desktop. Do you manage?
Can we?
No, we're sorry.
Can you see the slide?
We cannot see. No. No, we don't see anything yet. We can share it on your behalf. No. So did you follow the steps?
Can you see them now?
No.
Yeah.
Would you like us, Angela, maybe you can help us here? Would you like us to share on your behalf?
My bad.
Okay. We'll share the slides on your behalf for you, and then you let us know when you can see them. And then you must just prompt us to move from one slide to the next slide, okay? Can you see them on Remo? Kamogelo, can you see them on Remo?
Kamogelo? Kamogelo, are you there? See,
Thank you very much. I can see them.
We can see them. You are welcome to go ahead. Thank you very much.
Okay. Good. Therefore, I'll be presenting my honors dissertation in the response by a student. Next slide, please. Next, yes, okay. Onion is of economic value and is loved for its flavor in preparation of stews and salads. However, effects of climate change, acid-based biostimulant have gained in growth and yield. Over amino acids can induce by improving the photosynthetic nutrients and water utilization response in plant. Phytostim contains 22 free amino acids from moringa. There is a need to optimize the concentration of phytostim biostimulant for applying it. Figure 1 shows phytostim. The aim of the study was to determine concentration of on onion crops. The objective of the study was to investigate the effect of plant growth, bulb size, onion growth, and a microplot. Next slide, please. Materials and treatments, arrangements, and design. From Mayford seed was used for that. The set design was randomized complete block design. 4 by ranging from 0, 1, 3, and 6 applied. It had constant per concentration. However, was by every 7 weeks from week 1. Next slide. Picture A shows how seeds were planted using hybrid media, and planting was picture B indicate the growth and the technology which were raised under conditions. Next slide. Picture shows soil pasteurization machine used to pasteurize soil at room and 100 degrees Celsius for 45 minutes. While picture B indicates the soil ratio of 2 loom, 1 sand, 1 hydro mix, and they were mixed together using soil mixing machine. Next slide, please. Figure 4, picture A show how we had growth medium before onion planted. While picture B demonstrates onion crops planted in pots and the layout of microplots on picture C. Next slide, please. Statistical analysis. Data was subjected to analysis of variance using SAS, mean separation, and by means significant difference of 5%. The result of figure 5 show growth with crops as a result of plants, including untreated. However, enhanced group and system of onion crop as a result of effect ratio. 100% in failed to improve of high application of estimates, which resulted in poor growth and development of leaves and roots. Next slide, please. Show the graph length of different. How hence roots effectively to supply adequate water and nutrients to the onion crops. However, were not effective to improve the roots growth as a result of overdose application. Figure 7 shows the graph of leaf length of different concentration of biostimulant. However, biostimulant was applied as a foliar application with a significant role in the onion's life cycle. However, indicated positive response of growth and leaves free from deficiency symptoms. 106% biostimulant indicated negative to overdose application of biostimulant of insufficient growth, leaf rust, and next slide, please. Show the picture of vertical bulb size concentration by stimulant. which concentration was suitable as compared to untreated, including 3% and 6%. Next slide, please. The mass of different concentration of biostimulants. However, 1% of biostimulant had positive results as indicated, high vigorous plant with healthy leaves, 3% and 6% of biostimulant. Next slide. Can show the graph of different concentration factors which indicate that 1% higher size as compared to 6% and untreated. Next slide. Message estimate improved root length, leaf length, bud size, and biomass of oil crops. This information can farmers improve food security in ever-changing climate conditions in South Africa. Next slide. Research is recommended on potential as synthetic organic biostimulant. Lastly, can be utilized by both small-scale and commercial growers to sustain the yield and the quality. Next slide, please. Conditions, secondary metabolites and nutrition analyzed to determine the effect of phytostimulant with respect to the crops. Next slide, please. To acknowledge the University of Limpopo for accepting me to do my honors degree, and also Department of Science and Innovation for funding the study. And also, I would like to acknowledge SAAB for accepting my performance platform. Thank you very much.
Thank you very much, Kamogelo. You made up a lot of time there. There is one question from the audience, and you are welcome to speculate on that. If you don't have a clear answer, we would like to know what your thoughts are. The question is, do you think it is correct to refer to an amino acid-based fertigation as a product as a biostimulant? In other words, do you think it is correct to refer to this biostimulant? Rather, shouldn't it just be a nitrogen fertilizer because it contains only amino acids? What are your thoughts on that? Are you still there? Are you still there?
Yes. Another problem. Can you just repeat what you have said?
Okay. There's one question from the audience. The audience wants to know, is it correct to refer to this amino acid-based fertigation as a biostimulant? Do you think it's correct to refer to it as a biostimulant because it only contains amino acids and therefore might be viewed only as a nitrogen fertilizer?
The amino acid biostimulant can only be referred as a phytostim biostimulant. It cannot be referred as only a biostimulant.
All right.
Thank you.
There's one more comment. Let me get to that. There's one more comment from one of the audience. What do you define as a biostimulant?
A biostimulant is a substance. Define it.
Yes.
How do I do a define?
How do you define? Yes. Because it links on to the previous question.
Okay, a biostimulant is a substance that when it's applied to the plant, it stimulates the natural process to enhance the nutrients uptake and also to improve the plant to resist any abiotic stress. Thank you.
Okay. Thank you very much. Thank you for your talk. I would like to thank all the speakers in this session for their talks, and I would also like to thank the audience for their patience with our technical problems in the beginning. It seems that we sorted it out all from there. And then the next session will start after the lunch break, which is 1 o'clock. So thank you very much, and enjoy the rest of the day.
Same to you.